Okay,
yes, great.
Okay, so all right. So thanks, Jen, for the invitation. I've seen really great talks and a really good digital twins coming from the technical side, from medical side, and artistic side. So it has been really great. And the last talk from Rui has been really good. We use some of this information for Gaussian processes when we do. I'm not going to show today, but we do what's called history matching in reservoir simulation. So that has been one of the ideas. So that has been really good. Anyway, so let me the talk today will be a glimpse what we are doing in digital twins for reservoir simulation. This is some work with my students, and part of this work is joint with Ulysses Braganeto from the electrical engineering. And I need to thank Tamids for one of the pilot projects that we are working on. It's part of that funded pilot project on that. So let me start with what has been happening in petroleum engineering in general, right? So petroleum engineering has been what I call at the crossroads. And by the way, I'm Eduardo Gilden. I'm a professor here in petroleum engineering department. I think I forgot to introduce myself. Right? So petroleum engineering, as you may have seen in the news for the last year, 2 years, has been at the crossroads. What I mean by that, there's a lot of talks and regarding if you should move up to renewables, if you should stick with oil and so forth. And so I singled out basically two magazines here, one from 2021, both from 2021, that basically they say there's been a rush to net zero emissions. But the problem is a little bit more complicated than that, right? It's a little bit more complicated than that. And as you might expect, we depend a lot still in fossil fuels, right? But in the petroleum sector, there has been a lot of changes in the last 10 years. Right, and I'm I'm here placing another article from a JPT. JPT is our main magazine, technical magazine, and another things inside this magazine. But there has been articles on that talking about this energy transition, and one of the things that they point out is that energy digitization, it is one of the main things that is coming to the energy sector in general, right? Not oil and gas, but energy sector in general, right? Energy digitization. Here, another article talking about the demand for a digital, let's call digital engineers, right? Energy engineers, right? And here they say that there's lots of interesting problems in the energy digitization and digital twins and other things. And there's a shortage of people capable of doing that line of work, right? But as I said, the digital transformation in the oil industry has been happening for a long time, if you think about it, right? Of course, I mean, we're all talking about the energy or the industry 4.0 and so forth, and that has been happening in the oil and gas as well, right? The digital twin may be one of the forms of energy digitization. However, data science, data analytics has been coming to play a lot, especially one talk about safety, environmental, and issues. Trying to reduce the footprint of a particular oil field and so forth. Okay, the digital twin concept as well. It's not new in petroleum engineering, right? People have been doing digital rigs for maybe 10 years now, right? If you look at this as a rig, I believe this is a North Sea rig, but people have been constructing those digital twins in this particular case for only looking at the rig operations, right? What I'm going to show to you that goes beyond rig operations is that what is down below here that goes into the subsurface. Right? But as far as the energy goes, you have digital twins in the petroleum engineering, digital twins in windmills, try to reduce energy consumption in cars production, as was presented before in manufacturing, and so forth. So the digital twin, at least for the energy sector, it's not new. And there is a paper here that I placed here that talks about the success of in the last 10 years. That was in 2018, right? But what I do what's called a reservoir simulation. Okay, and basically, what is a reservoir simulation? Reservoir simulation, it is basically trying to come up with the flow in the subsurface. I mean, you can think about a computational fluid dynamic type of thing, but it's a computational fluid dynamic inside a porous media. What I mean by porous media, inside this block of rock here, imagine that is a huge block of rock. Okay, let me just go back one time. If you go this huge block of rock, you have a porous material, and fluid changes from places to places within those pores. Okay, so trying to produce hydrocarbons from this, it is hard because we need to account for many things that is inside this reservoir, things that we don't know. In particular, you see here a map of permeability. And permeability is just it talks about a conduction between fluid between the pores. It's a measure between that. And what you see in the yellow colors are high permeability, so fluid will move faster in this direction. And what you see in the blue colors are low permeability, fluid will not move to that. So here is an example of what I call a digital twin, is in reservoir simulation. Right, it's operations. You can have wells, you can drill wells. You see these production wells as you go along on the production, and you can as well drill injector wells, places that you're going to inject water or CO2 to sequester CO2 into this reservoir. Right, so a reservoir simulation by nature, it is a digital twin. Right, so what is hard about it? It is that if you want to simulate things in real time, as we are talking about now, right? This involves a lot of computational effort, right? Especially when we have a data integration, as you measure things out of this reservoir, let's say production out of these wells, you don't know exactly what is the properties at the subsurface. We're trying to infer those properties, right? So data integration is one issue, and to simulate this in real time, it is really hard. Just to have an example, this is by no means a big reservoir model here. This is by no means a big reservoir model, but it is a model that has about millions to tens of millions of what we call states, places that you're trying to find the solution at, and simulating this, it is hard, right? Not only that, simulating is one thing, but if you want to try to make this as a real-time operation, we also need to account for how we're going to optimize those wells. What I mean by optimize locations of these wells, optimize how you're going to produce those wells, right? How much water you're going to inject, how much CO2 you're going to inject, right? So it's really hard. So just to have an idea, I don't know why this is moving. Just have an idea. Here we have a case of 25 wells. If you have a 5 years of production times 12, we have about 1,500 variables that we need to optimize in real time. And optimize in real time meaning simulate this in real time, and has 10 to the 8 states. So what's possible now for simulating this in real time? One of the enablers, it is exactly model reduction, a data-driven modeling. In the morning, you saw the talk from Gino Ragusa, that he mentioned something about that. So I'm going to go a little bit on that direction as well. And model reduction, it is just a framework for getting a proxy model out of this big system. Okay, so why would you want to do that? Because moving towards this net zero emissions, we need to simulate these things in a real time way. Okay, see here you see an example of a hydrocarbon extraction. You see here an example of injecting CO2 into the subsurface. You see here an example of trying to mitigate emissions, maybe a methane emissions or something like that. And you see here storing hydrogen not only in tanks, but you can store hydrogen in the subsurface as well. Okay, getting to simulate these things, it is hard. Okay, and of course, I mean, petroleum engineers on the subsurface, you should be able to do this and optimize in a robust and fast way to get an answer. Right? So simulating those models is hard, as I mentioned. But what has changed in the last 10 years or so is that now there's an abundance of data. Okay, and I mean lots of data. We see now terabytes and more than terabytes of data, zettabytes, if you will, of data being processed that we need to process this real time. An example, and I'll show to you a picture of this. This is a fiber optics that goes inside a well, and you can have measurements of the state of the well for kilometers and kilometers of distance. Here you see a real-time operation of a reservoir and has real-time data that one can operate with. If you look at the drill bit nowadays, a drill bit can have sensors inside the drill bit. And as you drill, you can actually look at the lithology of the rock as you drill. Okay, so imagine how much data this is generating. Right? So again, within data, model reduction, and a combination of data and physics to infer something out of this reservoir. Okay, here, as I said, here's the work of Kildare, one of my students, doing and trying to infer fractures from fiber optics, right? So we have a monitoring well, and you have an operation well here. And this, I'm not going to show much what he's doing, but what I want to point out, just to get data in this what's called distributed acoustic sensing, it involves terabytes of data. So we need to do something with that. Okay. All right. So coming back to reservoir simulation. What is reservoir simulation then? I pointed out to you what is basically what we're trying to do. Mathematically, what we're trying to do, we're trying to solve this partial differential equation here that involves fluids in porous media. And to do that, we need to operate on the wells, which mean the controls can be pressures, can be the flow of those wells, and we need to determine what is the state of that reservoir, which means what is the pressure inside this reservoir, what is the fluid saturation, can be oil, a fluid, can be gas, a fluid, can be water. So we need to get the state of those guys. Okay, and what we can measure the flow. Oil flow, you can measure water flow, gas flow, and measure pressures as well, measure temperature, measure anything that you want inside the reservoir. Okay, so what is the approach that we do to make this simulation faster? Okay, so what we do, we take what we call the full order model and we evolve that into a much smaller subspace. I'm not going to go into details how we do that, but basically what we're looking for a surrogate that looks like this, okay? That has a form of a reservoir, right? What I mean, it has still a form of the equations of the reservoir, okay? But it lives in this XR leaves a much smaller subspace than X. And R here may be hundreds or thousands instead of millions or billions. Okay, so that's basically what we are looking for. Okay, so let me go to we've done some work on the physics-based reduced order modeling, and here's an example. Right, here's a hydraulic fracturing processes. We have two wells here on the top, and you have a bunch of hydraulic fractures to this well, and we can simulate this guy. Let me just point it out to the solution with a 50 times faster using our reduced order models. Okay, so 50 times, and in some cases even 100 times faster. Okay, now physics-based reduced order modeling is good, but it's not robust. And when it works, it is beautiful. When it doesn't work, it doesn't work. right? So there are a lot of investigation on for physics-based reducer modeling that we're still working on. It's very open area still. Okay, so what we are doing then, alternative work, how to handle all these nonlinearities. That why work when it doesn't work is because of so many nonlinearities associated with the fluid flow. Okay, so how do you handle that in a more data-driven type of work? Okay, so what we do, we look for alternative ways of expressing that equation. Okay, and again, I'm not going to go over the mathematics, but what we look for a type of linearization of that equation, a linearization of that equation. Okay, and in this particular way, here we look for a bilinearization of that equation because it has lots of nice properties. Right? One can create that non-linearization by operating what's called a Koopman operator. A Koopman operator is basically running a deep neural net to find that a particular operator. And again, I'm not going to go into details, but one can find that by just running a deep neural net to find the operator. And once you find the operator, then we linearize, we bilinearize, we can use the approach that I used before and create the reduced system right here. Okay, so that's basically what we are doing. See here, let me show you an example here with a toy example. Okay, so you have imagine that you have this 2D reservoir, have one producer here, another producer here, and we have one injector in the middle, right? All they're going to see, it is fluid moving from the producers to the injector. So you're going to see fluids moving from the producers to the injector. So here is the solution. If you see on the left-hand side, we have the full order model. On the right-hand side here, we have the reduced order model. Okay, and you see fluids moving from, this is fluids moving to the producers, from the injectors to the producers. Okay, so here you go. So moving from the center to the to the corners. And what is impressive then, it is that this guy, get an error of very few percent. Okay, so let me get to the solution here. So we are using a particular reservoir simulator here in developing MATLAB, but if you look at the solution here, that's a toy example, so it's not very hard to do it, but it takes 45 seconds to do it. If you look at two of our proxies, it may take 8 seconds or it may take 0.15 seconds, depending how you do that. But what's important is that if you're going to use this for a uncertainty quantification, as I mentioned in history matching, right? We can do thousands of those simulations in very few seconds, very few seconds. Okay? Of course, there are issues, and this is not always solvable. That's not always solvable, and we're still investigating. And one way that we are investigating, we are going back to the basics. Okay, I have just 1 or 2 minutes, so let me just finish up. Going back to the basics is to look at what's called a Buckley-Leverett problem. So what is a Buckley-Leverett problem? It is if you're injecting water, or if you have a displacement of two fluids, okay, it can be water, it can be any of the two fluids. This displacement is governed by this equation here, which is a hyperbolic partial differential equation. And to solve that involves lots of tricks. Okay, and one of the issues with solving this, displacing one fluid to the other, is because this fluid creates shocks. And if you don't deal well with the shocks because of these nonlinearities, right, you're not going to get a good solution. And that's what you see here. Okay, so we need to mitigate that. And in order to mitigate that, we are investigating how to do it by looking at what Ulysses in electrical engineering has developed, using his a special form of training or pins, right, that one can find a artificial viscosity directly from data. Okay, again, I'm not going to go into details, but basically we can train this partial differential equation directly from the data to find exactly when the shock happens. Okay, and if you know exactly when the shock happens, you can fix that equation and you move on to your reservoir simulation. Okay, so right now we haven't implemented that yet in the full reservoir simulation scheme, so that may be our next step. Okay, but let's just to conclude. Bean can estimate, physics-informed neural nets as deep learning and so forth, can estimate shock front without prior knowledge of the reservoir. The operation of Koopman bilinear and balanced truncation seems a good approach, right? But we're not done yet, right? There's some really good work happening. We want to get to the reservoir characterization and certain quantification. And once this is well trainable, and we know for sure it's robust, we're going to move on and enhance our digital twin operations using very fast proxies. Okay, so that's all that I wanna talk about. And if you have any questions, just let me know.